Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. In this video, we're going to answer the question, how do I design a recursive solution? You've come across this term while learning to program. We're going to look at recursion in Java, but the principles are the same in any language. Recursion is a way to solve a repetition or iteration problem, a problem that repeats. You may already be familiar with using loops to solve a problem that repeats. When you solve a repetition problem with a loop, you use a structure built into the language, such as while or for, that tests a condition, and if it's true, goes into the loop, executes the code in the loop body, and then always returns to the condition. The loop executes each time the condition is true. When you solve a repetition problem with recursion, you write a method, or if you're solving the problem in a different language, you might call that a subroutine or function or procedure. In a recursive solution, the method calls itself. So if I am in method print numbers, there is at least one call inside print numbers to print numbers. Just as with a loop, you will write a condition that tests if the repetition is over. If it is not over, you call the method again. In recursion, you are responsible for making that repetition code execute again by invoking the method again. Whereas with while and for, returning to the top of the loop is built into the language. Let's begin with a very simple problem so we can go over some basics, and then we'll look at a slightly more complicated example that is also foundational to understanding recursion. Let's write a recursive method that prints the numbers from 1 to 5. When we're designing a recursive solution, we ask the same questions we ask for a loop. What is happening recursively? When are we recursing? When are we stopping? How do we move the condition from recursing to stopping? We know that in our program, we are printing a number. That is what's happening recursively. When are we recursing? When the number we're printing is between 1 and 5. When are we stopping? When the number is greater than 5. How do we move the condition from recursing to stopping? We can increment the number by 1. How do we do that in a recursive method? Our control variable will be passed to the method as a parameter, and each time we invoke the method, we'll want to advance that variable toward ending the recursion. We can see that the number we're printing is the control information for this problem, so we should advance it each time we invoke the method. And we know that to advance it, we'll increment it by 1 because that's going to mean we will print the next number in the sequence, and it will move us toward the number being greater than 5, which means we're done. Here's what one version of this code might look like, called print numbers. This is in a class called recursion examples, which I've uploaded to my GitHub repository. There's a link in the description. I've chosen to write this in a way that highlights a principle of recursive programs. There is a test, an if statement inside a recursive method that separates how the method behaves for a base case versus a recursive case. Let's talk about those terms. A base case means we're at the end of the recursion and we should not call the method again. A recursive case means we haven't reached the end of the recursion, so we should advance the control variable and call the method again. Let's look at the parameters. I have two integer parameters, current and stop, and I have a test for the base case, current equals stop. If current is equal to stop, then we're done. In that case, we're not going to call the method again, but we will print current. Not calling the method again ends the recursion, so if we're in base case code, then the recursion will end. In the else, we have the recursive case. Here, we're not done. Current is not equal to stop. Now, I am making some assumptions about the way this method is initially called. If this is initially called with stop greater than current, then this method is the recursive equivalent of an infinite loop. Not good. You can prevent this from being called with bad parameters by wrapping this method in a method that calls it. I'll link another video on recursion here that talks about that, but you should not worry about it for now. Let's look at the recursive case. We're printing current. Now again, it's not our stop number. When we're writing the recursive case, we should imagine we're somewhere in the middle of the process. So let's pretend current is 2. We want to print 2. The last time through the method we printed 1, and the next time through we'll print 3. We need to make that happen. We need to invoke the method again, and next time we want it to print the next number. We do that by invoking the method again, but instead of passing current, which we're imagining is 2 this time, we're going to pass ++ current, which would be 3. Be sure to increment with the prefix increment so the variable gets incremented before it's passed as the parameter. The call stack is an integral part of recursion. You will see that in the next example. Let's get ready for that next example by seeing how the call stack is involved with this example. We start with main on the call stack. From main, I'm invoking print numbers for the first time, print numbers 1, 5. Now I'm going to show you something I don't usually show in my call stack drawings, but it is part of the frame on the call stack, and it is very important to understand, and that's the program counter. When we leave main for print numbers, the program counter is recorded in main's frame. The program counter is the line number we were on when we left the method. So I'm going to put 24 on the call stack next to PC for program counter. This is where execution resumes when we return to this method. A frame for print numbers is put on the call stack, and current has the value 1, and stop has the value 5. In the method, current is not equal to stop, so we go to the else, the recursive case. We print current, 1, and then we invoke print numbers again, but this time passing plus current, which is 2, and 5. And we also record the PC, which is 19. Again, that is where execution resumes when we return to this method. We aren't finished executing this method yet, just as we weren't finished executing main when we invoked this method. We're not done until we return from the call we just made. The frame for main and this invocation of print numbers remain on the call stack, and we invoke print numbers again, placing another frame on the call stack, this time with current equal to 2 and stop equal to 5. And in the method, current is not equal to stop, so we go to the recursive case, print 2, and then invoke the method again, this time passing 3 and 5. Another frame on the call stack, not the base case, so we print 3 and invoke the method again, this time passing 4 and 5. Another frame on the call stack, not the base case, so we print 4 and invoke the method again, this time passing 5 and 5. Okay, now current is equal to stop, 5 equals 5, so we are finally in the base case. We print 5, and the method is done. After the if code executes, we reach the end of the method and we return. Java pops this frame off the call stack. Now we're back in the prior invocation and we return to the PC, line 19. That was the call to print numbers. There's nothing else to do here, so this invocation is done. This frame is popped off the call stack. For each invocation, there's nothing else to do after the call to print numbers on line 19. So we continue to pop frames off the call stack and return until we are on line 24 in main. That is the last executable line in main right now, so the frame for main is popped off the call stack, and the program is finished executing. Now I hope you see the parallels to loops here, and your comfort with loops helps you design a recursive solution. The control variable or variables come in as parameters. You write an if statement to determine if you're done recursing, and if you are, you don't invoke the method again. But if you're not done recursing, you invoke the method again, but updating the control information before or while calling so that you will eventually be in the base case. Now let's level it up a little and make use of the call stack to accumulate a result. Suppose instead of printing the numbers, we want to add them. If we are doing this in a loop, we have an accumulator or gatherer variable, which we start at 0, and each time through the loop, we add the number, current in our example, into the accumulator. And you can write a recursive solution by passing an accumulator as a parameter. For my final example, I'll show how to solve the addition problem that way, and I'll explain why you might choose to use an accumulator. But with recursion, we can use the call stack as a sort of accumulator, and this can lead to a very elegant solution that provides a closer equivalent to some problem definitions, such as a factorial problem, making the solution more readable. So we're going to explore this form of writing a recursive method. Recall that in the last program, once we had reached the base case, we returned from all of the recursive calls to the line on which we'd called the recursive method, line 19. The recursive method was the only code on that line, so there was nothing left to do there, and the method ended. The frame got popped off the call stack, and eventually we got back to main. But what if we returned a value from each call and did something with that returned value, such as added it to the current value and returned that? Each time we return, we'd be returning the accumulated value, starting with the base case. This method is called add numbers, and it also takes control information as parameters, current and stop. you can see that it is very similar to print numbers. We have the test for the base case, if current equals stop, and we have a recursive call in which we increment current when passing it to the recursive call. But there's a big difference. In the base case, instead of printing a value, we're returning current. That will be stop. So if we're passing in 1 and 5 when we invoke this, when we reach the base case, we're returning 5. Now look at the recursive case. We're returning current plus whatever is returned from the last call. So if we imagine calling this method with 1 and 5, which I am doing in main, then we end up with a call stack almost identical to the one from the print numbers method. Main and then 5 frames for add numbers on the call stack. Now we return from the base case call, and instead of just returning, we're returning a value. That means that the call in the prior frame evaluates to that value, 5, just as any method that returns a value evaluates to the returned value. And the PC says we're returning to line 8. Line 8 says return current plus the last call. So the last call evaluated to 5. Current in this frame is 4. So now we're going to return 9. And we find ourselves back on line 8, this time in a frame in which current is 3, and our method call has evaluated to 9. So we return 12. Back on line 8, and in this frame current is 2, and the method evaluated to 12, so we return 14. And in the final frame where current was 1, and the method call evaluates to 14, we return 15 to main. I have that embedded in a print statement, so 15, the sum of the numbers from 1 to 5, is printed. When you're designing a solution like this, it helps to think in terms of the current value and the rest of the values. If the current value is 1, I want to add 1 to the rest of the values. So that becomes current plus add numbers plus current stop. If the current value is the base case, then I have to think about how to handle the base case so the result will propagate back properly. Here that is to simply return the current value. That process is a simplification, of course, because you have to design it correctly, but it often is a helpful way to think about it. Now, let's just briefly design a tail recursive solution and talk about why, in many languages, you will want to use tail recursion, which can be a slightly less elegant form of recursion. The print numbers method is an example of tail recursion, in which the recursion is the last thing to happen in the method. After print numbers is invoked on line 19, nothing else happens. The method is done executing. That is tail recursion, and it can be optimized by some compilers to prevent the stack overflowing. Java does not optimize tail recursive methods, at least at the time that I'm recording this video, although some Java architects have said it might in the future, others have said it might not. Add numbers is not tail recursive because once we return from the recursive add numbers call, we must still add the return value to current. So the recursive call isn't the last thing in the method, therefore not tail recursive. To make the add numbers method tail recursive, we could add into an accumulator that we pass as a parameter. Down at the bottom of this program, I have a method called add numbers tail. And again, you can see it's structured very similarly to the other two methods. But there's an additional parameter, total. And I treat that like an accumulator in a loop. When I invoke the method from main, I pass in 0 to initialize the total variable. When I invoke add numbers tail in the recursive call, I add current to total. So the first time we invoke the method, total is 0 and current is 1. And then on the first recursive call, current is 2 and total is 1, 0 plus 1. And on the second recursive call, I've added current to total, so current is now 3 and total is also 3, 2 plus 1. And on the third recursive call, total is 3 plus 3, or 6, etc. I've made some slight changes here. I can't increment current when I pass it, because it is then incremented when I add it to total, throwing my total off. So I pass current plus 1 as the next value for current. And the base case is also different. We're not using the call stack to accumulate, so I want to add the last number into the accumulator and return that, total plus current. For functional languages and other languages that optimize tail recursive methods so that they can't blow the call stack, you'll want to master tail recursion. And for reading elegant recursive solutions that align closely to problem definitions, particularly in languages like Java that don't optimize tail recursion, you'll want to master the kind of recursion that uses the call stack as an accumulator. I hope these examples move the needle on your understanding of recursion and how to design recursive solutions. In my experience, this is a paradigm that might involve a lot of practice before you have that aha moment, and it is suddenly all crystal clear. I promise you, it will come if you stick with it. Again, the code for this example is available in my GitHub repository with a link in the description, and I've also included a link to an auto-graded practice exercise so you can practice writing these methods. As always, have fun and keep coding.